Good morning. In the last class we have learnt Runge-Kutta method for solving initial value problems, which is a single step method, and we have learnt second order method. So, now let us see how higher order Runge-Kutta methods can be developed, and further we will see how to solve higher order equations as well. So, let us talk about last time we talked about second order. So, now let us go one step ahead, that is third order. Okay. So, that is 3 stage Runge-Kutta method. So, that means we are using 3 slopes. Okay. So, we define the method as follows. W1 K1, W2 K2, W3 K3, where K1 is f of x y, K2 A2h y plus A21h K1, K3 A3h y plus A31h K1 plus A32h K2. So, I would like to make a remark here. Sometimes in some books K1, K2, K3 will be defined with h in front, in which case this h will be taken out. So, that means if you multiply h inside, so h K1 will be the new K1, h K2 will be new K2, h K3 will be new K3. Okay. So, now how do we determine the coefficients W1, W2, W3, A2, A3, A21, A31, A32. So, total how many? 1, 2, 3, 4, 5, 6, 7, 8. So, one has to compare with the Taylor series method and then try to determine the coefficients. Since we are using 3 stage method, we expect that we should equate terms up to h cube. Okay. So, for second order method I have shown you the detailed calculation. So, I expect that if one would follow those detailed calculations, then we arrive at a system. So, now we have to make some arbitrary choice. So, I make the following choice, say A21 is A2, A31 is A3 minus A32. So, that means 1, 2, 3. Okay. So, with this we obtain system of equations as follows. So, the system of equations, the weight coefficients, they satisfy this, then so I repeat again, by choosing the above arbitrary coefficients, we get system, and that system has been reduced using this arbitrary. Then this will be the reduced system. So, this should be an exercise for you to obtain this system. So, once we get the system, what are the standard methods? One can have arbitrary choices, like in second order method we had different choices. For example, alpha is something and beta is something, half and half, so things like that. Okay. So, one can have arbitrary choices, but unless you show that the method is really sensible, we do not make any arbitrary choice. So, there are a couple of standard methods. So, what are they? So, the first one is Horn's method. So, we make the following choice. And A2 is 1/3, A3 is 2/3. So, you may see. So, this is A2, we made a choice, then A3, A3 2. So, 3. So, that will determine A2 1, A3 1 and in turn W 1, W 2, W 3. Okay. So, this is the set. So, this yields the following method. Since W 2 is 0, K 2 goes off, but then we need K 2 to compute K 3. So, this is a K 2 and K 3. So, this is Horn's method. Okay. So, you can see to define K 2 we are using K 1, to define K 3 we should have used K 1 K 2, but since W 2 is 0. So, K 2 does not explicitly appear. Okay. So, K 1 K 2 this should have been K 1 K 2, but okay. So, now we have other choice as well. Okay. So, that is more standard or K 3. So, in short notation I am writing. So, for this what is the choice? So, this is a called standard and this yields the following method. Correspondingly, K 1. So, A 2 H, A 2 is half, therefore, half H. K 3. So, please observe the way we have defined that led to this kind of. So, this is the first time we are coming across a minus sign in this. This is because we made an arbitrary choice. So, what was our arbitrary choice? Our arbitrary choice was A 3 1 equals to A 3 minus A 3 2. Okay. So, looking at these values, A 3 1 is A 3 minus A 3 2. So, this is 1 minus 2 which is minus 1. So, therefore, this we get a minus sign. Okay. So, how did we arrive at these methods? We have defined an approximation, then we consider the Taylor series expansion of the exact, and then we consider the H expansion of the approximate formula and try to match the terms. And since we are using 3 slopes, so we have gone up to that. Okay. So, how to obtain the coefficients? I left it as an exercise. So, I am sure mimicking the second order method one can obtain the system. Okay. So, now let us proceed for the fourth order method. So, this is a fourth order RK method. So, we define yes and K 1 K 2 K 3 So, for K 3 K 1 and K 2 are used, K 4 A 4 1 A 4 2 A 4 3 okay. So, this is our definition. So, this is in line with the general method with L slopes. Okay. So, now again our duty is to compute the arbitrary coefficients up to some accuracy. So, how do we do? Again we do this expand Taylor series and H expansion and compare. Okay. So, again I am leaving this as an exercise. So, when we do this we obtain the following. It is a lengthy system. Okay. Then it is getting nasty as we proceed. It is really very lengthy, but it is worth understanding because fourth order RK method is very popular and most of the calculations are done using fourth order RK method. Okay. And we have an additional condition which we get this standard condition sigma Wi is 1. This is also one of the equations out of that, and further we have more equations. So, they are okay, and it is a big and we have one more. So, I will try to write it here. So, it is a very big. Okay. So, this is a system we get, and again one has to look for arbitrary coefficients and then try to get specific method. Okay. So, what are the standard choosing A 2 equals to A 3 equals to half, we get okay. Then W 1, W 4 once, A 4 1, A 4 2. So, this will define the method as follows. K 2 f of So, this is the coefficients and then the method. So, this is our fourth order RK method. Okay. So, let us of course, the algebra is very tedious and we have done second order. So, if we try to follow we get the corresponding third order and fourth order methods. Okay. So, now we should try to see what happens to the error in each case, because we did not talk it. We will talk about this a little later. So, before we go further, so let us try to solve a problem. Okay. Is 1 and h is this. So, let us say calculate y of 0.1, sorry, y of 0.2, because h is 0.2, y of 0.4. Okay. See what is our So, what is x 0? 0, then h is 0.2. So, this will be x 1. So, essentially this is y 1, this is y 2. Okay. So, let us try to compute. So, we have to compute. So, f is minus 2 x y square. Okay. So, we should try to compute k 1. Obviously, our n is 0, we are trying to compute y 1, therefore, n is 0. So, k 1 okay. So, the given from here y 0 is 1, right. So, y 0 is 1. So, what is this? K 1 is minus 2, x 0 is 0 and y 0 is 1 square. So, this is 0. K 2 is minus 2 x 0 plus h by 2 y 0 plus h k 1 by 2 square. Okay, because k is defined as x n plus h by 2 comma y n plus h k 1 by 2. Okay. So, this is what we get. So, this is equals to minus 2, x 0 is 0, h is 0.2. So, we get 0.1 there, and y 0 is 1 and k 1 is 0. So, this is 0. So, we get 1 there. So, this will be minus 0.2. Okay. Then k 3 minus 2 x 0 plus h by 2 y 0 plus h k 2 by 2 square. So, minus 2, this already we computed 0.1 and y 0 1 plus h by 2 and k. Okay. So, k 3, right. So, this will be minus 0.2 1 minus. So, this will be 0.1. So, this will be 1 minus point not 2. So, this is 0.2 times 0.98. So, k 3 we have the value. Okay. So, this is our k 3, right. Then k 4. So, k 4 is defined as minus 2 x 0 plus h y 0 plus h k 3 square. Okay. So, k 4 is x n plus h should be there. Okay. So, this is minus 2 x 0 is 0, h is 0.2, y 0 is a 1, h is 0.2 and k 3 is minus 0.096 square. Make a pardon. No? So, this is a square missing here, okay, square missing. So, square. So, this value is incorrect. So, we get a new value, okay. So, we can use it. So, and accordingly this is incorrect, okay. So, we get k 3 is some x, then k 4 is some y, okay. So, then we get y 1 equals to y of 0.2 equals to y 0, that is 1 plus h is 0.2 times k 1, k 1 is 0, 2 k 2 plus 2 k 3, k 3 was x plus k 4 some y. So, we get the answer. Make a pardon, I have one, we have to simplify and get x and y, okay. This is just to explain the method, okay. So, that is how we compute the solution, right. So, now having learnt third order and fourth order RK method, we can try some more examples, but this is higher order method, okay. So far we have solved only first order initial value problem, that is y dash equals to f of x y, y of x 0 equals to y 0, right. So, now let us go one step ahead. So, can we use these methods learned to solve higher order initial value problems? So, what are the methods we have learnt? Let us say Euler method, Taylor series method and RK methods. So, can we use these methods to solve higher order equations, right. So, let us try to do that. So, higher order equations. So, we have first order IVP y dash equals to f of x y, okay, and y of x 0 is y 0. Then second order IVP. So, I would like to write standard method y double plus p x y dash q x y is some r of x, and since this is second order, to define second order initial value problems, the initial conditions we need 2. So, this is our initial condition, but here we need 2 condition because this is a second order equation. Y of x 0 is y 0, y dash of x 0 is y 1. Okay. So, how do we solve this? And we have learnt how to solve first order initial value problem. With that knowledge, can we solve second order IVP? Okay. So, the answer is yes, certainly we can. So, how do we do this? So, we try to do this by reducing the given second order to a coupled system of first order equations. So, how do we do it? Let us consider an example. Suppose the equation is y double plus 2 x y dash equals to 0 and y of 0 is 2, y dash of 0 is minus 1. So, this is our star, let us say. So, now can we reduce this to a coupled system of equations? Yes, of course. Let y dash equals to z, then y double will be, of course, x is our independent variable, y is dependent variable. So, now we have defined new dependent variable y dash equal to z, and hence y double is z prime. So, therefore, using this notation, star reduces to y double becomes z, and y dash becomes y double becomes z prime, and y dash becomes z. So, therefore, we obtain a coupled system as follows. Okay. Now, we need so now the dependent variables are y and z. So, we need the corresponding conditions. We have y 0 is 2 and y dash of 0 is minus 1, but our y dash is z. Therefore, this will be supported by z of 0 is minus 1. So, our given second order initial value problem has been reduced to coupled first order system. And where is the coupling? You can see y dash is z and z dash is related. So, this involves y. So, that means one cannot solve explicitly this unless we solve this and vice versa. Okay. So, given a system independently one can solve, or given a second order by reducing to coupled first order one can solve. Okay. So, let us try to learn how to solve a system using Euler method and if possible RK method. Okay. So, solving a system of equations using Euler's method. Okay. So, consider the following system. So, here x is the independent variable, y and z are the dependent variables supported by the following initial conditions. Say h is 0.2. So, x 0 is 0, y 0 is 1, z 0 is minus 1, h is 0.2. So, these are our parameters. Okay. Now, we have to define Euler method for this system. Okay. So, if you recall, we have y n plus 1 equals to y n plus h times f. This was our Euler, right. So, similar thing for this system we have to write, but treating y dash equals to f of x, y, z, z dash equals to g of x, y, z, and y of x 0 is y 0, z of x 0 is z 0. So, this is a general system. So, we know f and g. Okay. So, now for this we have to define Euler method. Okay. So, how do we do? So, we define y n plus h and for z g. Okay. So, now our h was 0.2. So, for the given example, for the given example, f is this, g is this. Okay. So, let us write down our f is x plus y z, g is all that we need is this. Okay. So, now let to compute y 1. Okay. Y 1 equals to y of 0.2 equals to y 0. So, let us repeat all that. X 0 is 0, y 0 is 1, z 0 is minus 1, h 0.2. So, y 0 is 1, h 0.2, and we have to compute f of x 0 plus y 0 z 0. So, that is x 0 is 0, y 0 is 1, z 0 is minus 1. So, this is 1 minus 0.2, this is 0.8. Okay. 0.8. Then z 1, which is z of 0.2, is z 0 h. So, we have to have g of x 0, y 0, z 0. So, g is y 0. So, 1, x 0 is 0, z 0 is minus 1. So, this whole thing is this is 0. So, 0.2. So, this is minus 0.8. So, that means we got y 1 and z 1. Now, let us proceed one step. Y 2 0.4 is y 1. So, y 1 just computed. So, let us have the data here. So, y 1 that was computed. Okay. And x 1. Okay. So, we need a we need y 1 plus h times f of x 1 y 1 z 1. So, y 1 plus h times what was our f? This. So, x 1 plus y 1 z 1. So, x 1 y 1 z 1. So, this will be okay. So, this equals so this is so we can simplify, we get and z 2 z of 0.4. So, z 0 sorry z 1. So, that is minus 0.8 h, then g of x 1 y 1 z 1, and our g was this. So, y 1 plus x 1 z 1. So, y 1 x 1. So, this will be so we get y 2 and z 2. So, this is Euler method. Okay. So, one can also try RK method, right. So, let us try to use maybe Heinz method, or maybe RK fourth order we can try. Okay. Right. So, another example, because there is a slight trick involved in solving a system for RK method. So, what is the trick? We will see. See, for example, you talk about Heinz method. So, what was the method? Y n plus 1 is y n plus h by 4 k 1 is f of x y, k 2 is x plus y plus Heinz method, but we have a system y dashed is x y z and z dashed is g of x y z. So, that means we need to define similar set, one set for this, one set for this, right. So, how do we do it? So, we define y n plus 1 is y n plus h by 4 k 1 plus, and k 1 is f of x y z. So, before we write for z, z n plus h by 4, some other notation, and L 1 is g of x y z, and k 2 f of x plus 1 by 3 h y plus 1 by 3 h k 1 and z plus 1 by 3 h L 1. So, this is the difference while defining RK method coefficients. This is the difference, because this is a two dependent variables. So, for y we are computing k 1, k 2, k 3, and for h for z we are computing L 1, L 2, L 3. So, therefore, in z the increment will be in terms of L's, and L 2 g of y plus 1 by 3 h k 1 z plus 1 by 3 h L 1. Similarly, k 3 is f of x plus 2 by 3 h y plus 2 by 3 k 2 and z plus h L 2 and L 3 2 by 3 h k 2 z plus 2 by 3 h L 2. So, you try to understand this, because this is very important while solving system. Since we have two dependent variables y and z, and since the system is defined as follows: y dash is f of x y z, z dash is g of x y z, where x is independent variable and y and z are dependent variables. We are defining one set for y and another set for z, okay, and this is the set. Okay. So, you can see, unless we compute one, we cannot compute the other. Okay. So, let us this time instead of taking a system, let us take y double plus with some conditions. Okay. So, let y dashed is z, then this becomes z dashed equals to x y minus 2 z from here, and y 1 is 1, z 1 is minus 1, and say h is 0.6. Okay. So, we have to compute say k 1. K 1 equals to, so what was f? So, before we compute, so we can write what is our f? F is simply z and g is x y minus 2 z. Okay. So, k 1 is, so now n equals to 0, k 1 is z 0. So, which is we can write x 0 is 1, y 0 is 1, z 0 is minus 1. So, this is minus 1. Okay. Then L 1, so we do parallel. Okay. Why we have to do this? Because to compute k 2, you need k 2, if it is function of z, you need L 1. So, unless you compute L 1, you cannot compute k 2. So, L 1 is g of x y z. See, L 1 is g of x y z. So, g of x 0, y 0, z 0. So, our g was this. So, therefore, x 0, y 0, x 0 is 1, y 0 is 1, minus 2, z 0 is minus 1. So, this is 3. Then k 2 is z 0 plus see, look, k 2 was defined as f of, so x y z dependency like this, but for the given case, since f is only z, so we get z plus 1 by 3 L 1. So, z 0 plus 1 by 3 h L 1. So, z 0 is minus 1 and h is 0.6 by 3 and L 1 is 3. So, this is minus 0.4. Then L 2. L 2 is g of, right, corresponding increments. What are the increments? X plus 1/3 h, y plus 1/3 h k 1 and z plus 1/3 h L 1. So, we have to have x 0 plus 1/3 h, y 0 plus 1/3 h k 1 minus 2 times z 0 plus 1/3 h L 1. Okay. So, this is a L 2, right. So, we can simplify x 0 is 1 and 1/3 h is this. So, 1/3 is 0.2. So, 1.2, then y 0 is 1 and 1/3 h is 0.2 and k 1 is minus 1. So, 1 minus 1/3 h is 0.2. So, let us write. So, 1/3 h is 0.2 and k 1 is minus 1. So, minus 0.2 minus 2 times z 0 is minus 1, 1/3 h is 0.2, L 1 is 3. So, this can be simplified 1.2 times 0.8 there, minus 2 times. So, this becomes plus minus 0.4. Okay. So, you get 0.96. So, this will be 6. So, this is a L2. Okay. So, now having computed L2, the next step is K3. So, K3 is Z0 plus 2/3 H L2. So, that is Z0 is minus 1 plus 2/3 H L2 is 1.76. So, this is minus 1 plus okay. Then L3. So, L3 is a little lengthy, x0 plus 2/3 H y0 plus 2/3 H K2 minus 2 times Z0 plus 2/3 H L2. Okay. So, we can get the value of so, for example, having computed K3, we get y of 1.6 equals to, this is our y1, the formula defined is y1 y0 plus h by 4 k1 plus 3 k3. So, y0 was 1 h 0.6 by 4 and k1 minus 1 plus 3 k3. So, plus 3. So, this is our so, this is minus sign. So, we simplify, we get the answer. So, this is the RK method for solving system of equations. So, the important remark is how to define the coupled system like this, the coefficients. So, this is very important in RK method. Okay. So, you can see here 2 dependent variables y and z. So, therefore, one system for one dependent variable, other system for other dependent variable, but they are coupled, and the coupling forces that you compute k1, then L1 will be computed. Unless L1 is computed, k2 cannot be computed. Unless L2 is computed, k3 cannot be computed. So, it is coupled in this sense. Okay. So, you may try the RK fourth order for a system of equations, which is definitely a little bit of algebra is involved. Okay. So, now in the next lecture, we try to learn, for example, somebody gives this is an approximate method, say RK method only, but how do you determine what will be the error corresponding to this approximation? So, that is an important task. So, we should try to estimate what should be the order of the error for a given approximate method. So, then we try to learn little bit of as I mentioned for computing y 1 some error is involved. So, now we are using y 1 to compute y 2. So, the error will be propagated. So, now if small disturbances are creating small errors in at early stage creates large disturbances, then definitely the system is not good for us, because such an approximation is not good. So, that means this is a concept of stability. So, we try to discuss all these things in the next lecture. Thank you.